Now, I just listed my Pythagorean identities in my notes, so you need to make sure that you've done that. And you have got to memorize all of these and even be able to recognize other manipulations of the formulas. Now, the reason we are studying these identities is because we need to get to a point where we can prove identities. But we need to come up with a basic skill of being able to simplify trig expressions first. So when I'm asking you to simplify a trig expression, you're going to be doing one of two things. You're going to be trying to either reduce the number of functions that's in the expression, or you're going to be trying to reduce the number of angles that's in the expression. You understand to simplify means it's going to not have as many terms or operations in it. Now, the ratio, reciprocal, and Pythagorean identities are used to reduce the number of the functions that we'll see. And the ratio and the reciprocal identities allow us to express all trig functions in terms of either sine or cosine or both. So I'm going to just get us started on what I mean by reducing or simplifying trig expressions. Only one angle is used in each of these expressions that we're going to try to work with. So what we're trying to do is reduce the number of functions that I see in each expression. Right now I see tangent, I see cosecant, and I see cosine. And that is just way too many to be working with. So my instructions say try to write in terms of sine and cosine. So I've already kind of started this one. Remember our ratio identity for tan, it's sine over cosine. You can take something and replace it with something that's equivalent to it. I'm using the reciprocal function here. Cosecant is 1 over sine, and I'm just making cosine look like a fraction like the other ones were. And then I understand that I'm working with fractions, so I can cancel out my sines, I can cancel out my cosines, and I'm left with the answer of 1. 1 is much simpler than tangent theta times cosecant theta times cosine theta. And how did I do that? I just wrote everything in terms of sine and cosine and simplifies. Alright, in the next situation I'm talking about, it says when a 1 and a squared function are involved in a sum or a difference, I'm going to be thinking Pythagorean identity. It doesn't mean that it's going to be a Pythagorean identity, but that should be the first place I'm searching. So I have cosecant squared theta minus 1. Cosecant squared theta minus 1. And I'm looking back over here and saying, do I have that? And I'm finding it right here. Cosecant squared theta minus 1 can be replaced with simply cotan squared. And that would be simpler because that's only got one term in it instead of 2. So cosecant squared theta minus 1 can be replaced with cotangent squared theta. And cotangent squared and sine squared. So I have the same angle. That's good. But I'm thinking, I believe I can express cotan in terms of sine and cosine, and maybe things will cancel out like they did in this first problem up here. So I remember that cosine goes on top and sine squared goes on the bottom. I'm trying to multiply that by sine squared. I like to make everything look like fractions. So cotan is cosine over sine, sine squared theta. So it looks like my denominators will cancel here, and I'm simply going to be left with cosine squared theta. That looks much simpler than what I started out with. So my point in this exercise is when you're seeing a 1 in some type of squared function, it doesn't mean it's going to be a Pythagorean identity, but that's somewhere to start. Okay, what do I mean when I say when given a related sum or difference? It's actually the same function minus 1, the same function plus 1. These are related, sum and difference. They're exactly the same except for a plus and a subtraction sign there. You know, just like you learned that a plus b times a minus b is a squared minus b squared, because the middle terms here cancel out when you FOIL. So that's going to be a nice remedy of simplifying when I have a sum and a difference. When I multiply here, I am going to get secant squared. This would be minus, this would be plus, so the middle term goes away, minus 1. So secant squared phi minus 1. Now, if I go and look back on my list, I'm wondering, does secant squared minus 1 anything? And there it is. Secant squared minus 1 is tangent squared. And y'all, we're just trying to become familiar with these identities right now. So I know you're going to need to look back over on your list until you are familiar, but we've got to do this. All right, in number 4, I'm thinking 1 minus sine squared theta. 1 minus sine squared theta. So I'm thinking I've seen that somewhere. Right here, 1 minus sine squared is cosine squared. Okay, so I'm going to replace that with cosine squared over cosine. Well, this term is squared, and this term is to the first power, so I would cancel here, and I'm just getting cosine theta. So I'm simplifying each part of the fraction separately, and then I'm trying to work with the entire fraction. So in this case, 1 minus sine squared reduced to cosine squared, so I was able to simplify the numerator. Couldn't do anything with the denominator, but then I could work with the entire fraction at that point. All right, let's look at the last one here that I have. It says, if you were trying to work with fractions, and trying to add them or subtract them, they've got to have the same denominator. So I look over here and I recognize this one has a denominator of cosine, this one has a denominator of 1. So if I want to have a common denominator, I'm going to have to multiply this by cosine theta over cosine theta. Then that's going to give me a common denominator of cosine. Up here I'm going to get cosine squared theta, because cosine times cosine is cosine squared. And then I have plus sine squared theta over cosine squared theta. I have a that's just cosine there. That's my mistake. I have a common denominator of cosine theta. And now I know that if I take my denominator, I can put it down, cosine theta. I can add my numerators. In this case, I really can't do anything except show that I want to add them. If you have fractions, you put down your common denominator and you add your numerators. But something in my head is telling me I've seen that today. So look back over here, and there it is. Sine squared plus cosine squared is a 1. So I can replace that with a 1. And I'm thinking, this looks like a reciprocal identity that I know. And so what is 1 over cosine? 1 over cosine is that one I made an error with a while ago. So that is 1 over, no it isn't, sorry. 1 over cosine is secant theta. So this is going to be secant theta. Now on your assignment page, I have asked you to study 2 examples that are in the book and add those to your notes also. So we're going to talk about a last set of problems I have here, and there's only 2 of these left. In this situation, I am working with different angles, and this should have been cotan theta. That was a typo on my part. This angle is theta. This angle is 90 minus theta. This angle is the opposite of x. This one is x. So in this particular situation, I'm working with expressions that need to have the number of angles reduced. And we're going to always be using either the cofunction or odd and even identities. So this one says the angles are different, use a cofunction identity. And the reason I know that I'm going to be using a cofunction identity is because that 90 minus theta or pi over 2 minus theta is setting me up for a cofunction identity. So I have cotan of theta and secant of 90 minus theta. The cofunction of secant is cosecant theta. That's how that works. The cofunction is secant to cosecant and 90 minus theta to theta. Now, I don't know what that is just off the top of my head. So I'm going to write everything in terms of sine, cosine, and see what happens. So cosine over sine makes cotangent, and secant is 1 over sine. This is that. Here's that. Are you following me? Then when I kiss and flip or multiply by the reciprocal, I will see that my sines cancel out, and all I'm left with is cosine theta. Okay. In this case, I should realize that I'm probably working with an odd or even because they are using that opposite of x there, and that's the only time I have an identity that works with the opposite of x. So that was the tangent of the opposite of x, where we have this with theta, but we would be using here. So if I want to take and replace the tangent of the opposite of x, it is the opposite of whatever the tangent is. Now when you get to this point, these are reciprocals, and you may just know that the product of reciprocals is 1. So my answer here is -1. Some of you may not understand that, so I'm going to write tan as sine over cosine. Should be an x there. And I'm going to write cotan as cosine over sine. Now I think you'll see how everything cancels out, and I'm left with -1. But up here, if you realize that tan and cotan are reciprocals, the product of reciprocals have to be a 1, and that's going to have a negative or opposite on that.